In this video, we'll take a look at an interesting theorem. It's called the Squeeze Theorem, but it has other names as well, like the Sandwich Theorem. So I'm sure you're wondering what this theorem is all about. And it is related to limits. And the thing that's different about the Squeeze Theorem, though, is that this is sort of an indirect way of evaluating limits. Right, so this is an indirect method for evaluating limits. And you'll see why it's referred to in this way. And it starts by looking at several graphs. So I'm going to draw a picture here. Hopefully this will help clarify this whole point. Let me identify an x value here, which we're going to call A, and then a y value here, which I'm going to call L. Now, I'm going to draw 3 graphs, and to make it very clear, actually, let me do one more thing. I am going to, in fact, I'm going to put a hole right there. So there's going to be a hole in my graph, or graphs. But the first graph, does something like this. And that graph I'm going to call h of x. And then I'm going to have another graph like this. And like that. And then that one I'm going to call g of x. And then finally this one in red. Looks like that. And I'm going to call it f of x, right? And one thing we can see for sure is that for values of x close to a, right? So if x is close to a, then this inequality is true. Notice that the blue graph is above. It's above the other two. The green one is kind of stuck in the middle, and then the red one is below the other two. So that means f of x is the least of the 3 function values, and then g of x is greater than f of x, greater than or equal to, and then finally h of x is greater than or equal to g of x. So we can see that as long as we stay close to a, because I don't know what happens further out down here on my graph or over here, but as long as I stay close to a, then this inequality here is true. So here is the statement of the Squeeze theorem. Right? And what it basically boils down to is, let's say we want to figure out the limit of g of x as x approaches a. But this is a very complicated function. It's not easy to handle either numerically or graphically or algebraically. But let's say f and h are functions that are easier to evaluate. Then if we know that f of x approaches L and h of x approaches L, so the function above and the function below approaches the same limit, L, then the function that's in the middle is kind of squeezed in the middle between the two, must also approach L. So that's the indirect nature, in that we want to say something about G, but it's easier for us to look at H and F. But certain things have to be true before we can do that. So if our inequality is true, right, whenever we're close to A, so where x is near A, right, and if we know that the limit as x approaches A of f of x is the same as the limit as x approaches A of h of x, which is equal to the constant value L, then the conclusion is, let me write it in limit form, then the limit as x approaches A of g of x, the function in the middle, the one that we really want, that has to be equal to L, right? So the concept of squeeze or sandwich is that you essentially have three functions, the one in the middle, right? So this inequality has to be true. The function in the middle is the function whose limit you really want to find. But the outer functions, the lower f and the upper h, are easier to work with. And if those two functions approach L, so the blue and the red, notice as you get closer and closer to A, all the y values on the red graph and all the y values on the blue graph, those are approaching L, then any function stuck in between the two must also approach L. All right, so let's take a look at a couple examples, and we'll do two. So let's look at examples. Let's look at this first one. And in the first one, I'll give you the inequality. So it is known that this inequality is true, right? So someone somewhere proved this inequality, right? It is known that the parabola 1 minus x squared over 6 is less than or equal to sine x over x, which is in turn less than or equal to 1 for values of x. Again, I'll say close to 0, right? So that's what is known, that's given to you. Here's the question: what is the limit as x approaches 0 of sine of x over x, right? So in this case, you know, if you wanted to label it, this was the lower function, the f of x, and this constant here is our upper function. This would be our h of x, and then the one that's stuck in the middle based on the inequality, this is my g of x, and that's the limit that we want to find, right? But if you look at it, let's say we didn't know this inequality, and I just gave you this limit and I asked you to compute it, right? And and I want you to do it algebraically, so I don't want you to use a table or a graph. Well, then if we take the limit as x approaches 0 of the numerator, well, the sine of 0 is 0. That's a trigonometric fact. Similarly, if I take the limit as x approaches 0 of the denominator, that's just 0. So we would end up with a 0 over 0 form. But, good luck trying to use any basic trick or technique from algebra or trig to simplify and reduce this, right? We can't cancel out the x's for sure. Well, what else? what else are we going to do, right? So we would be stuck if we were trying to use one of those direct methods for evaluating this. However, knowing this inequality gives us an indirect way, right? So what I can say is this. So let's take the limit of the lower function as x approaches 0, right? So if we take the limit as x approaches 0 of 1 minus x squared over 6, well, this is an elementary function. It's a basic parabola. We try to evaluate it, and we would end up with 1 minus 0 squared over 6, which is 1 minus 0, which is equal to 1, right? So the lower function here, as x gets closer and closer to 0, that lower function approaches 1. Okay, perfect. What about the upper function? So since this is true, and the limit as x approaches 0 of the constant, well, that's one of our limit properties. So the limit of this, oh, why did I write the limit again? This is equal to 1, right? So both functions, f of x and h of x, they approach 1 as x approaches 0. So by the Squeeze theorem, the Squeeze theorem, the function in the middle also has to approach 1. So the limit as x approaches 0, sine of x over x, that is equal to 1, right? So it's knowing two things: knowing that this inequality and for what values of x the inequality is true, and then knowing that you can call it like the lower function and the upper function, they approach the same value, then the function in the middle, by the Squeeze theorem, has to approach that value as well. So that's the indirect method that's being referred to. All right, so that's our limit. Let's look at a second example where it's another limit as x approaches 0, and this one is 7x to the 4th times the sine, and we'll use another trig function. Trig functions happen to show up a lot in a lot of these Squeeze theorem problems, right? So that's the limit that we have to compute. So if you notice here, there are two functions that we have. This function, a polynomial, and then this function is the composite of a trig function and a rational function. And we have a limit property for products. Remember, it says that if both factors have limits, then the product will have a limit. The problem, though, is, again, let's look at these two factors. So the limit as x approaches 0 of 7x to the 4th, that is 0, so that one exists. The problem is the other factor, the limit as x approaches 0 of the sine of, and then it's 2 over 5x. Well, if I plug 0 in there, I'm dividing by 0, so I have essentially something that's undefined, right? So essentially this is the sine of 2 over 0, and what on earth is that? So this factor doesn't have a limit, right? So the question is, what happens to the product? Well, because one of the factors doesn't have a limit, we can't use that direct limit property. So we have to somehow use an indirect approach, and the squeeze theorem gives us that opportunity. Now, for the squeeze theorem, we need an inequality. Now, one thing we know for sure is this. So this is, I'm going to write down a couple of facts about the sine function. So for all x, right, we know this is true. And you might remember this inequality from from trig, that your sine function is bounded between -1 and 1. So it just oscillates between those two, right? And this is true for all x. Now, what happens if you, for instance, have a composition of a function where the x is in the denominator? Well, what we can say is, for all x not equal to 0, that fact is still true. Like if I have something like this, and I'll write it in there, the 2/5x, that will be less than or equal to 1. So as we get close to 0, we know that this inequality is true, right? So I'm going to write that down, because remember, we can't evaluate it at x equals 0, but as long as we're close to 0, which is what we want to be able to evaluate this limit, we can say that this inequality is true, right? So let's write it under our, or as a part of our solution. So for values of x, and again, I'll say close. Like, what do we mean by close? Again, that's part of our intuitive ideas of limits. So for values of x close to x equals 0, right, this inequality is true. Your sine function is a bounded function. As long as you stay away from any I'll say like problem values of x, right, without getting too technical, then this inequality must be true. So now what we can do is, your 7x to the 4th, right, for values, in fact, for all values of x, 7x to the 4th is greater than or equal to 0. So since that quantity is positive, and if I multiply this entire inequality by a positive quantity, I don't have to change the direction of the inequalities. So this implies, so multiplying this part by the 7x to the 4th, I'll get negative 7x to the 4th. Multiplying the middle part of the inequality by 7x to the 4th will give me the function whose limit I'm trying to find. So 7x to the 4th times the sine of 2/5x, and then multiplying this by 7x to the 4th gives me 7x to the 4th. So what we can say now is, using this fact from trigonometry, we were able to come up with this inequality. And this is the type of inequality that we need to apply the squeeze theorem. So now what I'm going to do is use this function as my f of x. This is the function of interest. So this is my g of x. And then the upper function now is this one. And this is my h of x, right? So even though, we're given this limit and we were not given the inequality, we could figure out a standard inequality based on this result from trig, this property of the sine function, right? So let's evaluate the limit of the lower and upper functions now. So since the limit as x approaches 0 of negative 7x to the fourth. Now we have an elementary function that we can plug in 0 and evaluate it and get an answer, since that's equal to 0. And let's do the same for the upper function. So the 7x to the fourth, so that's 7 times 0 to the fourth. That's also 0. So h of x approaches 0, f of x approaches 0 as x approaches 0. So that means our desired function, which is stuck in the middle, also has to approach 0. So since these two things are true, by the squeeze theorem, right, so by the squeeze theorem, the limit as x approaches 0 of 7x to the fourth times the sine of 2 over 5x, that is also equal to 0, right? And we have to be careful, and the reason why we couldn't just use our standard limit property for products is because one of the factors, right, has the limit does not exist, right? But the product overall has a limit of 0 as x approaches 0, right? So those two examples kind of illustrate the types of problems that we typically apply the squeeze theorem to. Either one, you're given an inequality, which is a little bit easier, or the typical inequalities that you're expected to use involve knowing that the sine function and the cosine function, they always oscillate between plus or minus 1. And then what do you decide to multiply by? Well, that depends on what is asked in the question. So because this particular example had an additional factor of 7x to the fourth, that's why we multiplied everything by 7x to the fourth, right? So that's our squeeze theorem, a useful tool that allows us to evaluate limits indirectly.